Well, I wanted to get you an update, what we're up to and where we're going. We've just completed a validation of the next to the last feature. We've got one more feature that we're working on, and we're still getting it ironed out. What I'm using now is another back to the breadboard for the base controller. And when we're done with everything, all this testing, and we get this blue button to do what it needs to do, which is make the sounds, then this will be ready to be engineered into a container, a package. And it'll go into this. I've shown you this before. This is the container that it'll go in. So that's the LED display where you see this is the base. We're on channel 6. That shows you the speed. If I ramp it up, you see the speed showing 30, 40, 50, 60. Okay. If I change directions, it goes forward. If I hit the emergency stop, you'll see that it goes on. And then there's a red light over here now that is on. And if I hit the white button for reset, we can now reset the emergency stop. So we've got direction, speed, emergency stop, and the display. And the display is going to be on the handheld. We're debating on if and where we could put anything on the machine, but we may have to do that another day. So this is the ESP32 for the handheld. This is an identical ESP32, and that goes into the engine. It will go into the tender of the engine like it is here, configured here, okay? This has all of this stuff right there, okay? So that's been packaged. You've seen that hauling trains around. We had some interesting information on that coming back, so we wanted to make sure everything was as good as we can make it. So we're beefing up the code, putting in a little extra safeties and recalls, and we will finalize this as soon as I can get the blue button to go, okay? And well, I just showed you this engine here. It's running forward and reverse, and if I hit the red stop button, you'll hear it, boom, and it stops. Okay, I hit the reset, takes off again, everything's fine. And we're going to use that button signal to put sensors in front of the engine and notice if there's anything on the track, the engine stops. It could be another train, a cow, a cat, we don't know. But if something's in front of the engine, we want it to stop, since this motor controller is has a lot more torque power or torque potential, so we want to be careful. And this now then gets packaged, or is packaged, for the tender. Now we want to look at it for the diesels. Can we put this in an ALCO, or is it going to need a B unit to fit in? And then we're looking at our new engine, the Piercer class engine. Hasn't been really spoken about loudly, but we're working on concepts for that. And we've got a chassis on order from American Models. You may be familiar with their E8 unit. I have my Illinois Central E8. Here, let me shut this off. There we go. My E8 unit is here, and we're exploring the use of these trucks, not the body, but just the chassis and the drives. And we're looking at that to see if it will serve our purpose for the Piercer class, which may or may not be familiar with. A little background is there was a movie, Snowpiercer, in where it had an engine that was driving this train forever, perpetual motion, waiting for the ice age to thaw out. That's the story. And this engine was like amazing, okay? So we're thinking, what can we do? We want to build one. I want to build one. I want to build it. I just don't want to build a mimic of that. I want to build my version of that. And we've had some really strong feedback on how to do that, how to organize it, put it together, make it realistic, and how to power it exactly. We have some information here. Oh, here it is here under my 3 glasses. This is the 6 or 8 pages of software that goes into the engine part. But here's more of our code. Oh, let me sidetrack for a second because this is cool. We've come up with a notion of framework, controlling framework, where we have blocks, and blocks of code is identified, and then we have segments under that block. And I'll just be real quick with this. I won't make you too crazy, but here's a case where we have a block 2, which is the data structure and state, and then we have 2.1 right there, which is a packet definitions, and here's 2.2, which is the receiving message, receiving of the base message, the 6-bit message between the engines. So we want to make sure our radio is working. So we put all the code and protocols, but we put it in a way 2.1, 2.3, and it goes on, so that when we want to change it, update it, or see a problem, we can communicate among ourselves exactly where we think the problem is and how we want to address it. That has been maturing all summer, and yesterday and today we put our final tunes. As we're building in the sound, we knew we needed to make some adjustments, so we made those adjustments, and now the sound has its own block and its own segments, so that's going to work out really cool. So the notion of the piercer is, as it reads here, I'll read it, as conceived as a closed-loop, zero-emission powertrain using a Navy-grade micro-reactor, mated to a turbine generator and advanced traction electronics, and its purpose is to deliver perpetual power for humanitarian trains that bring water, shelter, and other things, medicine and health issues on Earth. So we want to be able to build a few of these engines in every continent, and then be able to go where we need to go with what we need to do to support humanity. It's a very lofty, it's a Star Trek-y kind of a theme. It's way out there, but I think we can make it realistic and fun, and as we go along, we'll be teaching how we're doing it. So here's the microthermal reactor. It's going to run around 600 C, so that's certainly enough to create pressure out of water. And then that's going to drive a hybrid turbine engine or generator. So it's going to spin a generator turbine that then drives a generator, and it's going to be putting out about 750 volts. And that's going to go down to a pair of traction motors that drive the wheels. We have some auxiliary power for all the other stuff, but we're inventing how we're going to do this with concrete possibilities. But we're not going to build it. We're going to build the model for it, okay? So our system could be built out, but you see what I'm getting at. It's a model built on what we think we want to do or what could be done. Anyway, that's where we're going. That's another story. But along with that, we want to be able to train and educate on the technology. I mean, these little boards are not new. They're out 3, 4, 5 years maybe, but they're not well received or not widely received, not widely understood. And they're somewhat complicated. I won't say complicated, clunky. They're clunky to engineer with. The clunkiness we think we can address with our framework of organizing how the software reads and looks and can be read and understood. And then we want to package this into the various engines, right? The steamers that we have, the diesels that we have, but we really wanted to carry it further because this module, and there's another one, somewhere, it's a real small it's what they call the mini, and it's very small, and we could package that into devices on the layout. Unloaders, like a robotic cargo unloader, could be, you pull in and you say unload one of the cars, and say the car has a side that pops down, and the loader would go in and pull out some load. We want to do that. Then we want to turn that into a learning experience where we teach how we built the loader, how we put the computer inside the loader, how we program it, and how we communicate. These little black flappy parts here are radio antenna. These guys are talking through radio, and they're only sharing 6 bits. 6 tiny little bits can do everything we need to do, even with sound. And we start adding other features. They're closed loop. They are going to leverage what we have: accelerate, brake, reset. Lighting can be separate. They're going to leverage everything we build into the base and engine controller, and it's not going to be another sensor and another wire and another. It's going to be very clean on the install. Had a K5, isn't it? It's going to be very clean on the install. And the tender, this can't do what he can do, and we have only touched, I think, 5%, maybe 5%. I mean, seriously, there's only 4 wires coming out of that, and that's a computer. 4 wires coming out of that MCU, motor control unit. We know we're just getting started in understanding and learning the capabilities. So this is what we're going to do. We're going to fit this into steamers and diesels. We're going to build a new engine based on this chassis. We're going to make it look cool, and it's going to have a lot of fun features, and it's not going to sound like anything you've ever heard. We've gone through the sound that we want. I don't think I have it noted here what it is or how it works. Nope. But I mean, it's a high pressure steam turbine is what you're going to hear. And as it goes faster, potentially speeds of 200 miles an hour, if we have the track. We were thinking about ways of using magnetic attachments to the track. I know on the Piercer, they had to put down planes. See the little wings there? They had to put down planes, so that pushed the engine down on the track. We may have to go something like that. In theory, in our model, we can do anything. But you got to realize you kind of want to run it too, don't you? And then the cars are going to be unique. That's a whole nother bag of tricks that we're working towards. There will be a car that has medical supplies, and it's going to get unloaded. And that's where we're getting the robotic unloaders, thinking how that's going to work, so that you can take it to a location and unload it and send the medical pods down to wherever the fire or the storms, whatever is going on. Anyway, that's what we're doing. I don't know why. I really like running these things crazy. This is the radio signal, and this is the CPU heartbeat, and that's just energy in the PC board itself. Yes, it has power. Yes, it's communicating, and yes, its computer is working. And yes, we have an emergency stop. And then we can hit this guy over here, and it resets, and everything's back to normal. Anyway, that's what's happening. Packaging, programming, finalizing, and then building what do we call the breakout boards, the PC boards that these sit on. These PC boards they sit on, I made. Those are just crap, those are just stuck together. Make it work is what I did. Now I'm going to have to design them so that when you plug these things in, you're going to have a socket with 6 wires. You plug it in. You're going to have another socket with 12 wires. You plug that in. That's how you get it together. Okay, that's what we're going to do. Big kit. The first big kit we're coming out with, I just worked on it. I don't have my sketch anywhere, but it's going to be a pair of trays, one for the handheld and one for the engine controller, and it's going to have voltmeters, knobs, LEDs, and it will fit one of these guys. It'll have these breadboard pieces on it, so if you wanted to do some of your own, you can, jumper and whatnot. We're going to have power generators where you can plug it into the wall and it will generate the proper power for the boards that you do. And these will be little kits like R&D. I mean, you put them together and you keep them and you use them forever. And then when you want to put something to put it in a train, you get another one of these $5 boards and another one of these $5 boards, and you take your program and you load it into those boards and you install it, and you still have your development kit that you can sit and play and start working on. If we're going to use drones, or are we going to use robotic trucks, or how are we going to get the loads off? How are we going to build the path for the loaders to go down? All that kind of stuff's got to be figured out. We're working on that too, but I think we can turn this into a learning experience, because there's a new idea of programming using tabular data. They call it parametric modeling, where we take X, Y's, and Z dimensions and put that in a table, and we feed that into the CAD system, and it converts it into a 3D part that you can print. The beauty of all of that is, if you want to widen it an inch or two, you go down to the part that says bench kit width, 8 inches. You go 8.5, and you touch it, and boom, everything that is impacted by the width is updated and adjusted, and the width is now 8.5, and you can print that part. So we've got a super good way to modify a part once it's designed by putting in these parametric tables. So what we're going to do is start our design with this bench kit and build that as a parametric table set that you can get and you print, or find someone that can print it. You go to the library and use their printer. This is all going to be on standard STL, whatever. And I think we're going to end up having a heck of a lot of fun. I'm having a lot of fun now. Anyway, that's where we are. It's a taste of where we're going, just talking you through it. There'll be a lot more going on as we get closer and closer. Got a little bit of paperwork to file, but it'll get there. And I'll keep you informed how we go week by week. Give you updates if you want. Just ask questions. Let me know what's on your mind. If you think this is an okay idea, does anybody want a piercer engine, or do they think they know they do? That would be so awesome. All right, I'll get back to you. Take care, guys. Keep trucking and keep teching. Later.